So hello everyone, this is lecture 36 for the quantum mechanics. In the last lecture we were discussing about the harmonic oscillator and we have derived the eigenvalues for the harmonic oscillator, that was this h cut omega lambda plus half. And we also find these two equations when we were discussing about the lowering and the raising operator. The first one was this: when a dagger will operate, it will raise the eigenvalue by 1, and when this a will operate, then it will decrease the eigenvalue by 1. So this was our lowering operator and this a dagger was raising operator. So we already find the eigenvalues. Now we need to find the eigenstates. But before that we were discussing that lambda can take only the positive values. So I already proved that. Then we discussed that lambda can take only integer values. So let's see what is the proof of this. So see, when there is this lowering operator, we know a will operate on lambda, it will go to lambda minus 1. So if we just plot this, there is this lambda on this axis, and now if there is any other value of lambda, like it must collapse somewhere because it can't be negative. So if at lambda equal to 0, we will see that after that there will be 1, 2, 3, 4, 5, 6. Means if there is some other number like 0.5, then after operating this lowering operator, it will go to minus 0.5. So that is not possible. That's why the last state should be 0. So if it is 0, then all others will be 1, 2, 3, 4, 5, 6. Only then it is possible for the one value. So that's why the answer, of course, is that at some point the application of A must kill the state, means this must become 0. So this can be 0 only when the all other eigenstates are integers. Otherwise this can't be 0. Like if you take 1.5, it will be 1.5 minus 0.5, then it can't be 0. It will be minus 0.5. So to make it 0, it must be 2, 3 and 3, 2, 1, 0. That's how it will go. So that's why all values should be integers. So lambda equal to 0 is an eigenstate of n. Then all other eigenstates will be 1, 2, 3, 4. That's how it will go. So we have find these eigenvalues h cut omega n plus half n, and n can be 0, 1, 2. Now we need to find these eigenstates. So well, let's see on this plot. These are your eigenvalues: half h cut omega, 3 by 2 h cut omega. So these will be like this: E naught, E1, E2. We call it as 0 point energy, then first and second and third. Now this n is called the number operator. Why we are calling it number operator? So let's see. There is this: if it is 0 point energy, then one sort that 3 by 2 minus half will give you h cut omega. One sort that you have one number of h cut omega, means one h cut omega greater than the 0 point energy, and 2 will give you 2 h cut omega greater than the 0 point energy. So that's how we call it as n, because this is giving us the number that how many times h cut omega it is greater than the 0 point energy. So n will 1 will give you 1, means 1 is greater, and for 2 it is 2 greater than 0 point energy, and 3 is 3 greater than, and that's how. So that's why we call it as number operator. If they ask you interview, you can tell that. So we call it, this is 0 point energy, and now 3 by 2 h cut omega. So h cut omega difference from this and this 2 h cut omega difference. So that's how. This eigenvalue has one quantum of energy h cut omega above the 0 point energy. So that's what I told you. Now see, there is one more thing to understand, that at n equal to 0, there will be no vibration, and still you have this half h cut omega energy. So how this energy is coming? Means we know in the solid state we studied about the phonons, and n equal to 0, there will be 0 energy state. So why we are getting this half h cut omega still when there is no vibration? So you can study that concept in the Casimir effect. Means there is some virtual photons concept that they will emit, and you know that energy can't be created or destroyed, but there is this uncertainty principle in the quantum mechanics, that is delta E delta T greater than h cut by 2. So this amount of energy can be produced, and the condition is it must be returned back in delta T time. So this uncertainty is possible. That's why this Casimir effect come into the picture. So you can study about this. This is a very interesting concept. So this is the virtual photons that will come from the vacuum. We also call them antiparticles. So that gave this energy when there is no vibration or no photon. So so let's now our target is to find the eigenstates. We already have eigenvalues. Let's find the eigenstates. So eigenstates of quantum harmonic oscillator. So for that we just operate this raising operator on the n. That will give you n plus 1, n plus 1. We already know this expression. That was lambda, lambda plus 1, lambda plus 1, and lambda is n. So, and if this n is giving n plus 1, n minus 1 will give you n. And now from here you can find this, we need to find this n, that is eigenstate. So from here n will be 1 upon root n, a dagger n minus 1. Now we need to substitute this n minus 1 also. So if you operate this on the n minus 2, it will give you n minus 1, n minus 1. From here you can find the n minus 1, this one, and substitute the value here. So n minus 1 will be 1 upon root n minus 1 a dagger n minus 2. So this will be, just substitute the value here and you will get 1 upon root n minus 1 a dagger square n minus 2. So see, this series will go on, means this next step, when you substitute for the n minus 2, it will give you n minus 3 here, and it will be n minus 1 n minus 2, and it will be 3 power. When then you substitute for n minus 3, it will give you n minus 4, and n minus 2, n minus 2, n minus 3, n minus 4, and a dagger 4. That's how it will go on. So the nth term will be given by, means this 2 will go to the n, so n minus n will give you 0 here, and this will be n minus 1, n minus 2, n minus 3, so it will be n factorial, and this will be a dagger n. So that's how you get your nth eigenstate. Now you have the expression for the eigenstate, but still this 0 or the ground state, ground eigenstate is unknown. So we need to find this ground state. So we already saw that this operating, the lowering operator operating on the 0 ground state will give you 0 because there is nothing negative possible. So we'll use this to find this 0 ground state. So we already know if the position operator operates on the wave function, it will give you xi, and momentum will give you minus I h cut del by del xi. So we'll use this expression. So let's see how. Now a, we already know the expression for the a operator, that is 1 upon root 2 under root m omega by h cut x cap plus iota 1 upon root m omega h cut p, and this ground state equal to 0. Now this will go to the 0, and let's simplify this. Just multiply under root m omega by h cut inside. So it will give you m omega by h cut x plus, and this will under root m omega will cancel out, and root h cut will give you h cut. So this will be this. Now x will operating on the 0. So you know x is operating on 0 will give you x psi, means this is our ground state. We are denoting it psi 0. So it will give you x psi 0, and this p will give you this p psi equal to p psi 0, and p is nothing but minus h cut del by del x psi 0. So we'll substitute this value and this value here in this expression. Then we will get this m omega by h cut x psi 0 plus I by h cut multiply minus iota h cut del by del x psi star is equal to 0. Now we will take this h cut will cancel out, and this I square will give you minus plus, this will be plus. So just take this psi star out, psi 0 out. So it will be m omega by h cut x plus del by dx psi 0 equal to 0. Now from here we just need to solve this equation to find the psi 0, to solve this for psi 0. So how can we solve this? Dx will go this side and psi 0 will go to this d psi. So this will be 1 upon psi 0, and d psi 0 equal to minus m omega by h cut x dx. Now this will give you x square by 2 and some constant c, and this will be log psi 0. Now from here you know what is psi 0 is. Psi 0 is nothing but a exponential this, and a is some constant, that is e to the power c. So you know this. Now you have the ground state, and to find this value of a, you just need to normalize this wave function. That will be psi star psi equal to 1, taking the integration minus infinity to infinity, and that's how you can find the value of a. So try to prove this value. A will be m omega by pi h cut raised to the power of 1 upon 4. So now you have the ground state, so you can find the first eigenstate, second eigenstate, and all. So a dagger 0 is, means you know a dagger, if this is the raising operator, so it is operating on the ground state, will give you first eigenstate. So just substitute 0, which we already find it, and here it will give you first, and then operating on the first will give you 2. So that's how you can find. So let's try to find the eigenstates. So after substituting the value of a, which is this here, so we are getting the ground state as m omega by pi h cut 1 upon 4 exponential minus m omega square by 2 h cut. So let's use this, substitute it here, and operate the a dagger on this. We will get 1. So let's try to find the 1. So a general expression will be, we'll use this expression for the general eigenstate. This means substitute the a dagger value. We know already this is our a, so a dagger will be minus iota here. So just put it here, and this is raised to power n. So this will be, means just substitute it here, in place of a dagger substitute it here. So we'll get this expression 1 upon root 2n n factorial m omega by pi h cut 1 upon 4, and this is complete nothing but a dagger raised to power n exponential minus m omega x square by 2 h cut. So this expression came, this one and this one is from here, and this is our a dagger, and if you solve you will get this. Now we need to find the first one, first eigenstate. So just substitute in place of n is equal to 1. So you will get 1 here, 1 here, and 1 here. So this is nothing but just multiply this inside. So it will be multiplied with this, and this is dy dx of this. So try to solve it. Is 2 steps, you can get this equation very easily. Now this is your first eigenstate. And now what is the difference between the ground state and the first eigenstate? You see that there is nothing power of x power is 0, but here you will see you are getting this x also. And that's how means you can find the second and third eigenstates also, and you will see that in general you will get the Hermite polynomial here. So we already studied about the Hermite polynomial in the differential equation, you can see there. So in general we can write for the nth eigenstate, psi n x is nothing but 1 upon root 2 n n factorial m omega by pi h cut raised to by 1 upon 4, and this is a Hermite polynomial hn nth polynomial and root m omega by h cut x exponential minus m omega x square by 2 h cut. Now you know what is Hermite polynomial. This is the generating function for Hermite polynomial, that is minus 1 to the power n exponential z square dn by dzn. This is nth order differentiation, exponential minus z square. So first is always 1, means for the first Hermite polynomial is 1, second is 2z, and then third is 4z square minus 2. So that's how it will, and in place of z it will be this complete term. So that's how you can find, means for the 0 you can say that it is 1, so this must be 1. So put it here 1, then you will again get the same expression as we find it here. So that's how it is described. Now for n equal to 2, means for the first one, if you need to find this one, so put h1 is nothing but 2z, so it means 2 multiply this whole term, so 2x this. So solve this, you will get again this one. So now you can find the nth eigenstate by yourself very easily. Now we can just simplify this equation more, just putting m omega by h cut as alpha square. So substitute in place of this alpha square, then here also m omega by h cut will be alpha square, and this is alpha x. So the equation will be reduced to this. This is a very easy expression now, alpha by and root pi 1 by 1 upon 2 exponential minus alpha square x square by 2. This is our ground state, and this is the general expression. If you put n equal to 0, this whole term will be 1 here, and it is, as h0 is nothing but 1, so you will get this expression. And in place of alpha, if you substitute m omega by h cut, you will get this expression again. So now we have all the eigenstates possible. Now let's try to plot them, all eigenstates. So we know this expression is simply a Gaussian function. So you know how to plot Gaussian function for different n, as depending on the Hermite. We will get for n equal to 0, it will be this kind of curve. For n equal to 1, we will get this odd kind of curve, antisymmetric. And for the n equal to 2, we will get this kind of curve. And see, this is not a sine curve. This part is very less as compared to this is higher, more higher as compared to this. So if you try to plot the probability, so this will give you some kind of this expression. This is a little bit higher than this, and this will give you probability. This will be like this, and here this part is lower than this. So here we will get some kind of this and little bit lower this. So this kind of thing. And for the n equal to 3, it will be lowering here, means the minima here, and you will get this kind of terms, means this kind of like this. So that's how. And the n equal to 3, this will be maximum at the center. And for the odd, for all the odd terms, you will get 0 here, and for all the even terms, you will get maxima here. You can see that. Now see, if we talk about the minima, for n equal to 0, there is nothing, no minima here. For n equal to 1, you will get 1 minima. For n equal to 2, you will get 2 minima here. So similarly, for n equal to 3, you will get 3 minima here. And for n equal to 3, there will be minima at the center, 1, and others will be 2 and 3, like this. For n equal to 4, there will be maxima at the center and 2 minima here, 2 minima here. So that's how you can calculate the minimas. Now there will be this kind of probability you will get. If n equal to 100 is there, then maxima will be at the center and 50 minima at this side and 50 minima this side. So this kind of curve means this is lowering, so a little bit lower. That's how you will get this kind of thing. Probability will be like this for n equal to 100. So now what we are seeing here, actually, this is when you know about the harmonic oscillator. And if we talk about in the classical way, then the probability of finding the particle is mostly at the end of the oscillation, means because at there the particle is most of the time, that's the probability is maximum at the ends. Okay, now you will see in the quantum mechanics, probability is most finding probability is nothing but at the center. So there is a totally complete opposite of each other in the quantum and the classical. But if we get to the higher number of eigenstates, means it is going very large, then you will see that this is nothing but again turning into the classical, and there is a probability is maximum at the ends. So that's how the classical and the quantum harmonic oscillator relates to each other. So you can see this. Now this topic is over. So there is one more topic before we will discuss the questions. That is half harmonic oscillator. So what is the meaning of half harmonic oscillator? That is means in the x less than 0, the potential is infinite. So if potential is infinite, then there will be zero eigen function here. There will be no eigen states, but eigen state will be only greater than s equal to 0. So now you will see, using the boundary condition, we know if wave function is 0 here, then at the boundary it must be 0. So for all the eigen states which we are having maximum at the center, they won't be possible in the half harmonic oscillator. Why? Because at the boundary it must be 0. So only the odd ones, these are becoming 0 here. Only the n equal to 1, n equal to 3, n equal to 5. So no even eigen states are possible. So that's why in the harmonic oscillator we will see that only n equal to 1, 3, 5, all these are possible. So there will be energy difference of 2 h cut omega. So you can write any eigenstate in the general formula. These all three formulas are same, giving the same value. If n dash can take value 0, 1, 2, 3, 4, 5, then we can write energy expression for 2n dash plus 3 by 2 h cut omega. Like n equal to 0 will give you 3 by 2, 1 will give you 2 to the 4th 3 7 by 2. And if n is, you are saying that n double dash is 0, 2, 4, 6, means it is even number, then you can write this formula in this way. And if n can take only odd values, then you can write this formula in this way. So all these formulas are giving the same values. These are 3 by 2, 7 by 2 and all. So that's it for today. We have completed the harmonic oscillator. Now we will discuss more questions, more and more questions, because that's how you will get this concept clear. So thank you everyone.